Hello everyone. This course will primarily focus on physical design flow, and this particular section will talk about the physical design flow overview. So for example, there are multiple steps in a flow. The first step is basically floor planning, and inside floor planning again there are two or three steps. Then there is something called as placement and routing, and inside placement and routing basically we call it as PNR. There are again multiple steps like clock tree synthesis, crosstalk, DRC clean, and so on. So this particular section will talk about the overview of the physical design flow, and the following sections will be taking each and every step into detail and trying to explain it in with the help of some lectures. Okay, so to start with, we'll be starting with the floor planning step of physical design flow. The first step of floor planning is to define the width and height of core and die. So in a chip, let's say if you have a square shaped chip, this is how the core and the die will look like. This is the core section, where why we call it as core, because this is the area where primarily your netlist sits, the core logic, basically any core logic, whatever the functionality and all, that will be sitting in this particular area. That's why we call it as the core of the chip. And the surrounding it after leaving some amount of space across the core, you see the die section. Okay, so this step will define the width and height of core and die. This is the height, this is the width. How do we come up with this particular square structure, or how do we decide the width and height of core and die? That will be covered in the following sections. This will be this section is just the overview of physical design flow. So the first step is to define width and height of core and die. Okay, the second step is to define the locations of pre-placed cells. I'll be talking about what is pre-placed cells in the following sections. For now, just assume these pre-placed cells are cells which have got certain functionality. For example, this block might function as an adder, this block might function as a multiplier, this block might function as a divider. So all these predefined functions are already encapsulated in these blocks. They are built separately, and those cells are called as pre-placed cells. We can give it a name as macros, we can call it as IPs as well. Okay, so these are the pre-placed cells. The second step is to define the locations of pre-placed cells. So the way the locations of pre-placed cells are decided is based upon their connectivity. For example, the block C has got most of its pins which are close to this side, and there are some pins which are sitting over here as well. So that this makes it easier for connectivity. That's how we come up with the locations of pre-placed cell. And there are many other things, we'll talk about that in the following sections. But this is the second step, where we define the locations of pre-placed cells, and the locations of pre-placed cells are decided based on their connectivity with the complete netlist. Okay, on which part of the netlist do they sit, and do they want to access the pins, access the boundaries very often, and so on and so on. So these things will decide the locations of your pre-placed cells. Okay, the third step is to, this is just a naming convention saying that these are our pre-placed cells. The third step is to surround the pre-placed cells with decoupling capacitors. So the concept of decoupling capacitors is explained in a separate section. It's explained as a part of crosstalk videos. Yeah, you might want to have a look into those videos. But the concept is basically this blocks and this blocks have got some internal logic. They already have got gates and flip-flops and clock cells which are sitting inside it, and they might switch very rapidly. So during a finite period of time, let's say this particular block switches at the same instant, and there will be a huge amount of current demand. So this particular block should be, this particular power supply which will be presenting in some time from now, this particular power supply should be able to cater to the power needs of these blocks when these blocks are switching from logic 0 to logic 1. So for example, when blocks are switching from logic 0 to logic 1, basically there are capacitors that gets charged, and these capacitors, how do they get charged? They take charge from the power supply, and this power supply should be able to cater to these needs. If they are not, there is a way that we can surround this with decoupling capacitors. So decoupling capacitors, you can consider them as power supply which already has got some amount of power already. We keep these decoupling capacitors charged, and whenever there is a current demand, or whenever there is a need for charge from this particular blocks, the decoupling capacitors will be feeding them. Okay, and for the remaining amount of time, the decoupling capacitors will itself get charged by the main power supply. So we have talked about this in a separate section called as crosstalk. You might want to have a look into those videos. Okay, so the third step is to surround the pre-placed cells with decoupling capacitors. So this is the steps that it will cover. So we have a D cap 1 in the top of block A, block B. We have D4 between block A, block B. We have D cap 2 and we have D cap 3. So we have surrounded the encapsulated the blocks with the decoupling capacitors. They are basically, you can also treat this decoupling capacitors as a coupling as a coupling element between the blocks and the power supply. Basically this decoupling capacity, so these blocks will now need not depend completely on the power supply. They can get their charge from decoupling capacitors. So all these are covered in very greater detail in crosstalk videos. You might want to have a look into them. Okay, next is power planning. This section also has been covered in the crosstalk videos, where we talk about the need of power planning, or the way the power planning has been done over here. So what we do, let me explain you what we do as a power planning. So we create a mesh kind of structure. Instead of having one source of power supply, we will have multiple sources of power supply. Assuming this color of the line is referred to as VSS, and there will be one more that will be coming, that is called as VDD, and let's call the cross as the contacts. So if you have this VSS lines, you see there are multiple VSS lines, and they are arranged in a grid fashion. Okay, and there are multiple VDD lines which are again arranged in a grid fashion. Okay, now any cell which is sitting over here will tap the power supply from its nearest power source and ground. Okay, and the reason to have this kind of mesh structure is because we don't want power to be coming only from one place. For example, if the traditional circuitry that we have, it has got a power supply sitting over here. It has got a power supply sitting over here, and there's some logic which is sitting over here. And this logic, whenever it charges or discharges, it has to take the power from the main supply. We are trying to avoid that kind of structure and creating a mesh structure where now logic which is sitting over here can draw the power from its nearest power lines. So these all things has been covered in greater detail in the crosstalk videos. You might want to have a look into them, where we explain that when this kind of situations might arrive. So this kind of situations might arrive when, let's say, thousands of logics are charging from 0 to 1, and they demand current at the same time. At that kind of scenario, the power planning structure, the mesh structure of the power planning is very helpful. Okay, so this is the next step of power planning. The next step is pin placement. So now any logic, any gate, any circuitry will have got some input pins and output pins. We have to identify those pins and place it somewhere over here in the die area, in the area between the core and the die. So these are the pins. So we have already a circuit, we have already a predefined circuit which we will be analyzing in this particular course. And from that particular circuit, we have got this pins which is D out. These are all the output side. So for the sake of simplicity, we have kept all the output pins on the right side, we have kept all the input pins on the left hand side, and these are the this is the way they have been arranged: D in 1, D in 4, clock 1, clock 2, D in 2, and D in 3. And there are reasons why we placed it in not in an ascending order fashion, but in location something like this. For example, if D in 1 is over here, D in 2 lies over here. So there is a reason we have done it, and we will be explaining that in the following sections. But the next step, the next step of the floor planning is pin placement. Okay, and the pins are also located close to logic that we'll be seeing over here. So we'll talk about how the pins are being placed, or the logic behind placing the pins, and what can go wrong and what can go right while placing the pins. If you play, let's say if d out 1 was not over here but over here, and d out 2 was over here, so what can go wrong? We'll talk about them in the following lectures. Okay, and finally you have a logical cell placement blockage. What does this do is this ensures there's nothing. We place a blockage in the area between the core and the die, which ensures that there will be no logic cells accidentally placed in this area, because these are only for the pins area. These are only for pin accessibility. Okay, so this is the logical cell placement blockage. It says that the name suggests that the logical cell placement blockage, whenever there is a logical cell and a placement blockage terms coming over here, it says that this particular area will block the placement of logical cells. So wherever you see this kind of thing, there will be no logical cells that will be placed over here. Okay, so that's the final step of your floor planning, and now your floor planning is ready for placement and routing step. This floor planning has been a very basic floor planning that we have been doing for the circuitry that we'll be designing in some time from now. So this is a very basic floor plan for for that kind of circuitry, but the concepts remains the same. For example, the mesh structure or the decoupling capacitors or the concept of logical cell placement blockage, this will be remaining the same from a smaller chip to a multi-million gate chip. So most of the concepts remains the same. Okay, this is just an overview of the small circuitry that we'll be trying to design. So what we'll do is, since I'm running out of time, our floor plan is already ready. We'll look into a placement and route overview. We'll look what are the steps in placement and route, only the overview part in this section, and the next sections will be talking in detail about each and every step of the placement and route. So let's try to do all this in the next video. Thank you.